Welcome back to the Deep Dive. Today we are taking an expert-level plunge into, well, one of the most foundational architectural shifts in modern high-speed silicon, the AMD Versal Network on Chip, or NOC.
That's right.
And we are specifically zeroing in on what you might call the power user's path, the advanced RTL-centric design flow using Xilinx parameterized macros, the XPMs.
Yeah, this is where the real fine-grained control happens.
So for context, let's just set the stage a bit. If you spent any time, working on complex FPGA designs over the last decade, you absolutely know the single biggest migraine is timing closure.
Oh, absolutely. Hours, days lost.
Exactly. As chips grew larger, transistors shrank. Those traditional soft AXI interconnects just became bottlenecks, huge bottlenecks.
You really did, consuming massive chunks of the programmable fabric, increasing wire resistance. It was getting tough.
And leading to those long multi-day compilation runs that, well, often failed to close timing anyway, especially when you had demanding high-speed I/O like DDR memory or PCIe trying to stretch across the whole device.
It was a physical design nightmare, honestly. It really stalled productivity for a lot of teams.
It truly was a physical constraint headache.
Yeah, and that's precisely why the Versal NOC exists. The core mission of this deep dive is really to show you how AMD fundamentally tackles that problem.
How they fix it.
Exactly. By moving communication entirely out of that congested, soft, programmable logic and into a dedicated, hardened, high-speed structure. So this deep dive is for you, the designer, the architect, who needs not just performance, but that ultimate flexible control you get with the modular NOC flow.
Okay, let's unpack this then. We're moving from fighting wire delay to optimizing logical packet flow. How exactly does this hardened IP deliver such a massive efficiency gain and crucially cut down on those punishing build times?
Well, it is a complete paradigm shift. It really abstracts away those physical challenges we were just talking about.
Right.
The Versal NOC is hardened, it's scalable, and it's configurable IP. You're essentially replacing those complex, custom-routed soft logic AXI interconnects.
The ones causing all the problems.
The very ones. Replacing them with a predefined, dedicated network infrastructure. So the moment you move your communication onto the NOC, you just stop worrying about interconnect delay scaling with process technology.
So the timing closure problem for that communication path just disappears.
It basically vanishes, yes, for that part of the design.
And when you look at the quantifiable results, compared to devices that still rely heavily on soft logic interconnects, like, say, some of the competing Agilex devices, the sources show Versal designs achieving significantly faster build times.
That's consistently reported.
And it seems like it's because the most complex long-haul routing problems are just completely offloaded from the physical design tools.
Exactly. The tools are freed up. They can focus on closing timing within the programmable logic blocks themselves, not between them over long distances.
That acceleration in iteration time must be huge for a design team.
It's a massive productivity boost. Absolutely. Now, structurally, you need to picture this network. It's quite a sophisticated device-wide mesh. It has two main components. You've got the horizontal paths, the HNOCs, which span the width of the device, usually near the high-speed I/O banks.
Right, near the edges.
And then you have the vertical paths, the VNCCs, which run the height of the device, and crucially connect adjacent SLRs, super long-range dies, right?
Got it. So this mesh provides these redundant, high-bandwidth pathways for long-distance communication.
Without ever touching the programmable fabric for the transport itself.
Okay, that makes sense.
And the traffic moving within this mesh is governed by something called the NOC packet switch, the NPS.
The NPS.
Think of the NPS as the high-performance traffic cop. It's a 4x4 router, and it supports up to 8 virtual channels in each direction.
8 virtual channels, wow.
Yeah, for managing different traffic flows. And what's fascinating here is the flow control mechanism. It uses a credit-based system.
Okay, I think I know this.
Yeah.
It's conceptually similar to TCP's sliding window protocol.
Very similar, yes. Instead of waiting for an acknowledgement, the sending MPS knows exactly how many packets or credits the receiving switch has buffer space for.
So it prevents congestion before it even starts.
Precisely. It manages the flow proactively.
And managing this whole complex device-wide mesh, is that distributed or?
No, it's centralized. There's the NOC programming interface, the NPI. It actually lives within the platform management controller, the PMC.
The PMC.
And it automates all the critical configuration routing tables, quality of service profiles during the early boot up sequence.
So the compiler does the hard work.
Right. The Vado compiler aggregates all the traffic specifications you define in your design and computes one single optimal unified configuration. The NPI just executes that plan.
So it's a true system-level optimization, not just local decisions.
Exactly. Very different from piecing together soft interconnects.
Okay, this device-wide structure sounds brilliant, but you still have to bridge the gap, right, between your custom logic, speaking standard AXI probably, and this complex internal packet network.
Good point. How do you get on and off the highway?
Yeah. How do we get our standard AXI transaction onto this mesh? That's where the gatekeepers come in, I guess.
That's a good way to put it. We need to talk about the interface layer. The NoC master units, or NMUs, for traffic going in.
Ingress.
And the NoC sleeve units, NSUs, for traffic coming out, egress.
NMUs and NSUs. Got it.
These units are absolutely essential. They are your interface layer. They handle things like clock domain crossing, ensuring your AXI data is correctly rate matched, and converting it into the NoC's internal packet format and back again.
Okay.
The NMUs, the master units, they come specialized based on their purpose. For general purpose masters sitting in the programmable logic, you typically use the NMU 512.
NMU 512, and that's the flexible
That's
one.
the most flexible, yeah.
Yeah.
Supports data widths from 32 bits all the way up to a pretty hefty 512 bits for memory-mapped AXI4.
Okay, 512. Then you see the architecture's sort of true intent with the more specialized units, right?
Exactly, like the HBM NMU.
For high bandwidth memory.
Right. It's restricted physically to SLR2, where the HBM controllers are, and it's specifically optimized for super low latency access to those HBM controllers.
And that one's fixed with.
It's fixed at 256 bits, yeah. No AXI stream support there. It's purely designed for speed and bandwidth to the HBM stack.
Makes sense.
And of course, there's also the fixed with NMU 128. This one is optimized for hardened blocks like the control, interface, and processing system, the CIPS.
Main processor system.
So this level of specialization across the different masters really shows they're trying to minimize overhead depending on what's driving the traffic.
Okay, that covers the masters going in.
Yeah.
Now here's where I think it gets really insightful, looking at the slave side, the NSUs coming out.
Yes, the egress path.
Most standard NSUs, like the NSU 512, they just do the reverse, right? Convert the NoC packet back into a standard AXI interface for whatever logic is receiving it.
Correct. Standard AXI out.
But the core performance advantage, especially for high bandwidth stuff like memory access, seems to be found in the DDR-MC NSU and the HBM NSU.
Yes. This is key.
Wait, so let me make sure I understand the performance implication here, because this sounds huge. These are described as partial NSUs. They convert the NoC packet directly to the memory controller domain, whether it's DDR or HBM.
Yes.
Completely bypassing the intermediate AXI protocol layer.
That's exactly right. This AXI bypass is, frankly, a stroke of genius in system architecture design.
Why is it so significant?
Well, think about it. When you convert back to standard AXI, you incur overhead, right? There's serialization, deserialization, the address phase timing, data phase timing, all that protocol stuff.
Right, the standard AXI handshaking and cycles.
By converting those NoC packets straight into the DDR memory controller's native protocol or the HBM controller's native protocol, you eliminate that entire protocol conversion overhead.
Wow.
Which means you achieve the absolute lowest possible latency and the maximum possible efficiency for memory access across the NoC.
So it really proves the Versal NoC isn't just a routing solution. It's like a finely tuned, heterogeneous network designed for maximum performance on these critical system resources like memory.
Precisely. It's highly optimized for those specific paths.
Okay, that's a critical detail.
Now let's pivot. Let's talk about the modular flow itself. This is really what separates, the experts from the standard users, maybe.
The power users we mentioned.
Yeah. Well, many designers might start, understandably, with the GUI-based IP integrator flow.
Which is great for getting started quickly.
Absolutely. But the modular NoC flow embraces RTL directly. Using these Xilinx parameterized macros, the XPMs like XPMs or XPMs.
So this is the pure RTL-centric approach.
It is, and it provides that fine-grained control. It's also highly scriptable, which is absolutely indispensable for large teams, automated build environments, or highly customized designs.
Okay, but hold on. If the Vivado compiler does all the heavy lifting, the routing, the QoS, the configuration, and the standard IP integrator flow, why would an advanced designer willingly take on let's be honest, the risk of manually defined TCL constraints and manual dress mapping in this XPM flow? What's the return on investment for all that extra manual effort?
That's a fair question. The ROI is control, ultimate control, automation flexibility, and the ability to manage complexity that the GUI flow sometimes just can't handle gracefully. Things like dynamic function exchange, DFX, for instance.
Defects. Okay.
But yes, you absolutely take on new responsibilities. It's not automatic anymore.
So what does that look like?
Let's maybe look at the 4 key steps a designer now owns in this flow. First, instantiation. This is straightforward conceptually. You directly instantiate the XPM templates AMD Vivado provides these right into your own Verilog or VHDL code.
Okay, standard RTL instantiation.
Right. You set all the required parameters on the macro, connect the physical AXI ports to your custom IP, that kind of thing.
Okay. Step 2.
Second, constraints. This is crucial, and it's entirely manual. You must define all the connections between your NoC endpoints using TCL commands in your constraints file.
Not just connecting wires in RTL.
No, you're telling the NoC compiler about the logical connection. The key command here is create a connection. This explicitly links, say, your instantiated NMU port to a specific target NSU port.
This is where you gain that control, maybe defining connections across different SLRs that a GUI might struggle with.
Exactly that kind of scenario. Or implementing very specific routing topologies. You have direct control via script.
Okay. Third step.
Third is address mapping. Again, manual. You have to define the aperture addresses. This isn't just setting a simple base address. You are mapping a specific range of physical addresses from the master's point of view to that precise NoC interface you instantiated.
So you're telling the network exactly where any transaction within that address range needs to be routed.
Precisely. In a complex system with multiple masters and slaves, this manual definition allows for guaranteed deterministic routing, which can be absolutely essential for specialized, high-reliability systems.
Okay. And finally?
Finally, validation. You use the dedicated validate nanot command before you run synthesis. This command is basically your sanity check. It ensures that all your manual constraints and address maps are coherent and implementable by the NoC compiler.
Catches potential mistakes early.
Hopefully. It's a vital step in this manual flow.
Right. And this is where the advanced nature really raises the technical bar, isn't it? You mentioned DFX.
Yes. This manual flow is pretty much essential for DFX, where you're dynamically reconfiguring parts of the FPGA fabric.
Okay.
If you're using DFX, you, the designer, must manually ensure the consistency of certain graphic properties. A key one is TDesDid. That's the target destination ID used within the NoC packet.
The destination identifier.
Right. You have to make sure it's consistent across your static logic and all possible reconfigurable modules that might be loaded. The tool itself can't always guarantee that the TDesDid defined in some reconfigurable module matches what the static logic expects unless you manually enforce that consistency in your designing constraints.
That immediately sounds like a potential pitfall, a trap for the unwary expert, maybe. You gain all this flexibility, but you absolutely have to assume greater responsibility for system-wide coherence.
That's a perfect summary. Increased control, increased responsibility.
And we should probably also mention the simulation limitation here. For all this power, there's still a bit of a wall, which is that no simulation, as of the sources we reviewed, isn't currently supported when a design uses an RTL top-level module with modern system Verilog interfaces.
Yes, that's a known limitation. Using system Verilog interfaces at the top level for connecting to the NoC XPMs complicates simulation setup currently.
That feels like a potentially significant limitation for expert teams relying heavily on modern verification flows using UVM and system Verilog interfaces.
It is a known limitation, and it often requires workarounds, like using Verilog ports instead at that boundary for simulation purposes. It reinforces that this modular flow is truly the expert path, warts and all, as you say.
Okay. But the power you gain through parameterization itself is immense, right?
Oh, absolutely. The XPMs perform that crucial abstraction trick we talked about earlier.
Right.
You, the designer, you only need to focus on your own IP's requirements. You define parameters like data width, which, as we said, can be 32 up to 512 bits for a memory-mapped NMU, and maybe feed width for transaction tracking signals on your AXI interface.
And the XPM handles the rest.
The genius is that abstraction, yeah. If your custom IP uses, say, a standard 64-bit XI interface, you just set the data width parameter on the XPM macro to 64.
Okay.
The XPM macro then handles the complex job internally. It intelligently packs that 64-bit data into the NoC's fixed internal packet width, which is typically 128 bits, sometimes 256 bits, depending on the path.
So you don't have to manage the 128-bit no-sacket protocol yourself.
Not at all. The XPM manages it for you. It completely decouples your logic's interface from the network's internal transport mechanics. That's powerful.
Okay, parameterization is one side of the performance equation, but the other half is making sure the traffic actually gets prioritized correctly through the network, which relies entirely on quality of service or QoS.
Absolutely critical. QoS. This is defined as a traffic specification, and it's used by the NoC compiler during that optimization phase. It's really composed of two main parts: the traffic class and the bandwidth requirements you specify.
Let's focus on traffic class. That dictates the hierarchy of the priority, right? Set at the NMU, the ingress point.
Correct. And there are three crucial classes to understand. First, low latency. Pretty self-explanatory.
For time-sensitive stuff.
Exactly. Reserved for transactions like maybe CPU access to shared DDR memory where you really need a fast response.
Okay, second class.
Second is isochronous. This is for traffic that has strict real-time deadlines. Think video streams, perhaps, where jitter and latency must be minimal and predictable, consistent delivery time.
Got it. Low latency, isochronous. And the third.
And finally, best effort. This is the default, really. It's reserved for non-time critical bulk transfers where guaranteed latency isn't the primary concern, maybe moving large data buffers for processing later.
Okay. And critically, we need to stress, the sources were clear on this, best effort is the only option available for HBM read and write traffic.
That is a key constraint, yes. All HBM traffic is classified as best effort, regardless of its actual urgency from a system perspective.
And that's where classification becomes absolutely everything, doesn't it?
It really does. Because the compiler, by its very design, prioritizes allocating resources, routing paths, bandwidth to the low latency and isochronous traffic first.
Right.
So a poorly classified best effort path, even if it's actually quite important to system function, could potentially get starved for shared NoC resources if there's heavy contention from higher priority traffic.
And that could severely impact overall system performance, even if the logic itself is fine.
Absolutely. It stresses the absolute necessity of doing thorough system-level performance analysis before you commit to hardware. You need to model the traffic flows.
Which is why AMD provides those cycle-approximate System C models and the more accurate System Verilog models, right? To help tune these traffic specifications.
Exactly. To help you understand the potential bottlenecks and tune those QoS classifications before you build the hardware, you are explicitly shifting resource management from the physical domain, fighting routing congestion, to the logical prioritization domain, managing traffic classes.
That's a fantastic distinction. A really clear way to put it. So, okay, to wrap this deep dive up, the Versal NoC, and specifically this modular XPM flow, it offers this unparalleled control. It enables designers to finally move past that, frankly, soul-crushing time enclosure fight.
It really could be.
And instead focus entirely on optimizing the logical data flow, the packet priority, achieving faster iteration, and hopefully guaranteed performance, especially on those long-haul routes across the chip or between SLRs.
Yeah, the true mastery of the Versal NoC, I think, requires understanding not just the RTL or the XPM parameters, but the complete system-level implication of your choices.
Bigger picture thinking.
Definitely. You have to master how QoS settings interact with potential contention points in the mesh and how those specialized endpoints, especially those AXI bypassing units like the DDRMC NSU we discussed, function to deliver that maximum throughput. The performance you get out is entirely dependent on the quality of your traffic specification going in.
That's the ultimate takeaway here, isn't it?
Yeah.
The design philosophy shift is profound. You're no longer just routing wires. You're optimizing packet traffic and defining logical priority.
Well said.
So, for you, the designer listening, maybe think about this. What aspect of your current system design, perhaps a cross-chip sensor interface or a massive memory access pattern, could benefit most from moving from being treated as a physical routing constraint to being managed as a logical priority system? And, just as a thought experiment, what's the first data width parameter you would change on an NMU XPM to match your logic exactly, knowing the NoC will handle the packing?
Interesting question to ponder.
Thank you for joining us on this deep dive into the Versal NoC and the modular flow. We'll catch you on the next deep dive.